Okay, finally, let's talk a little bit about the project for this course, which is worth of about 2 ECTS credits, which means it's a substantial amount of work, about 50 hours. If you're working together with somebody else, two person, it's total 100 hours or so. There are 3 different project options. First option is the data acquisition add-on design for Raspberry Pi. Second option is greenhouse automation option, and then third one is your own topic. But actually that own topic you need to check me first if it's feasible or not. Okay, so let's take a look at this first one, data acquisition add-on, what it is all about. So Raspberry Pi is if you haven't heard of it yet, it's probably this is not the project for you. But Raspberry Pi is an embedded Linux platform. There are hundreds of thousands of users, hobbyists using it. It's very powerful small device with ease of I/O and networking capabilities, and basically it's a very nice platform for several kind of applications. And what is the best part, it's practically a Linux computer. So if you are familiar with Linux, then it's quite easy to start working on it. The tools are also available, and best part of it's you can find lots of project topics for this one on the Raspberry Pi projects. Okay, one small thing is missing: analog to digital converter. So your project is to design a PSoC device that function as A to D converter for Raspberry Pi, and the communication protocol here is I2C bus. So practically that PSoC device is a analog to digital converter, multi-channel analog to digital converter device on I2C bus, so slave device. The task itself, this is quite straightforward, although it takes some time to work on it. So you would be creating a PSoC 5 project to function as a sampling A to D converter with I2C bus. And the minimum requirement, okay, at least 4 analog input channels, single-ended, and let's put, for example, 10 kilo ohm impedance for each of those. So practically you need to tie a input pin with a 10 kilo ohm resistant external resistor. 12-bit accuracy. So minimum requirement 12-bit accuracy for the A to D converter. Full speed communication on I2C. So 400 kilobits per second capable communication. 7-bit address, which is the standard addressing. Select freely, but document it also clearly. So if somebody else is working on it and has already a device with the same address on I2C bus, he or she can actually go and modify your design on that part. Minimum requirement is not much, so it's 10 samples per second. After downsampling, of course, you have practiced downsampling of data, so you can actually you know how to run a free running A to D converter and multiplex it, and then do boxcar averaging on each of those each of the channels. So you would be using one single A to D converter and an analog multiplexer. Again, you can freely select which pins are the analog sensor inputs, and yeah, as long as they are not in some other use on the PSoC kit. Then about the buffering, since this is a slave device, the buffer size should be enough to hold 1 second of data. At 10 samples per second, 12 bits and 4 channels, it actually is 4 times 10 times 2 bytes at least. And actually you also should have some sort of mechanism to avoid missing data, and of course document it clearly. If you just put those values on the this I2C bus to be read by some other device, then there is a chance that you are either overwriting unread data, or you are reading again the same data that which already was there. So find a nice solution, feasible solution for avoiding the missing data, and of course document it clearly. Okay, a hint. Actually, the kit program can also be used as I2C bridge. So there are actually instructions how to do it, or team up with somebody else and use another kit as the I2C master. That's another one. Or of course, if you have this this Raspberry Pi already available, then please use that one, since then you can already verify that your design actually works. Let's see, for debugging, okay, for an I2C. Okay, there. Exercise report return, or actually this is project report return. The same things as previous. You must document clearly enough for, okay, not for me now. Think of the Raspberry Pi community. You might actually, if you make a great design, easy to use design, you might get some fame on the Raspberry Pi community by then publishing it, but it's not required that you publish. But anyways, so keep your open mind that you might be actually publishing it for the Raspberry Pi community. Okay, minimum requirement. Minimum requirements are about the same, except instead of link to your main.c, I changed the last part, so it will be link to user guide. So instead of my main.c, of main.c, so you would have the user guide.pdf, which explains how a hobbyist can build and program the device and start using it. So there should be a simple user guide, wiring diagrams, command interface, if any, parts list. Okay, command interface you might actually have. Parts list with links to device datasheet, link to a short demonstration video. So all of these should be on that PDF file, and provide a link here. And remember to share the PDF on some cloud service so that it can be opened. Okay, so that's the big deal about the data acquisition system for Raspberry Pi. By the way, the Raspberry Pi does have ADC and DAC, but that's only for the uh, audio. So it has audio codec, which is actually working as the A to D converter, but okay for these audio samples only, not for sensor data. Okay, the second project topic, greenhouse control. That's a typical greenhouse what I'm talking about. Now I'm talking about a hobbyist greenhouse, which size is about few square meters, not really a huge. So I would say this is the maximum size greenhouse you would be building your own controller. Bigger than that would be commercial, and they have their own systems, and when they are doing commercially you will actually buy systems from the shop. But for this course there's plenty of good things that can be measured, and also plenty of good things that can be controlled. Well, not that many actually, but enough, but not too many. Okay, minimum requirements. So create a PSoC5 project to function as the controller for a hobbyist greenhouse. I'm not asking you to find all these electromechanical parts, since they can be costly, and also they probably would need some extra debugging to get them working. But anyways, first measurement is air temperature using digital temperature sensor, and the cost of the sensor is less than €5, single unit price on either Farnell or Mouser. Both of those actually have the worldwide distribution systems, and for example Mouser also sells to anyone who has money. Farnell is mostly for the you must have the VAT number. Okay. So and this measures, and then some control, measurement and control. Adjust a hatch. Hatch meaning an opening like this. This is a mechanical hatch what I have on my greenhouse, right there on the top of the door. Anyways, you don't need to think of that one either, since you can demonstrate the hatch opening by using, for example, that 9G servo what you already used on the second exercise. And basically, if temperature is greater than 20 degrees, open hatch 20% of east centigrade, meaning at exactly 20 C it's still okay, but if the temperature rises up to 25, then it's already full open. Okay, and that's practically a good setting what I have found on my greenhouse, which has these say thermomechanical openings. Okay, then at least in Finland, not necessarily in the Central Europe, but in Finland the spring actually is long, and if you want to start your the season early, then basically you need some heating, extra heating for the night time. So practically there should be a function that turns on extra heating. Okay, and that's basically means that single digital output connected to LED for demonstration. You don't need to turn on any extra heatings there, just demonstrate the control. So there should be a an LED lighting up. And then basically turns off that extra heating if temperature rises above 10 degrees, so that you don't need to heat it anymore. So hysteresis of 5 degrees on the control. Okay, then measures again relative humidity. Okay, we didn't have any relative humidity sensors here, so you need to find one, either funnel or Mauser. Okay, you need to also discuss with your local laboratory engineer or with me about the purchasing of those components if you don't want to spend that money from your own pocket. On the other hand, if you want to build your own small greenhouse, then that will be a good time to start a nice hobby. Okay, if you get this relative humidity sensor, it usually comes with also temperature sensing. Okay, this is again turns on something, meaning okay, you need to turn on a LED, an LED to light that. Okay, now it basically does something like water spraying. So basically, if the relative humidity drops below 30% relative humidity, then it's quite dry air. So then it needs some spraying, and basically it turns off spraying if the relative humidity rises above 80%. I put it this relative humidity quite. There's no need to go up to 90% relative humidity. Then you start having mold on the greenhouse. Okay, and then measure soil temperature with a digital temperature sensor. 2 sensors more. Okay, yeah, the same as in here, but no adjustment. This is used for only for monitoring use. For example, those one-wire temperature sensors or the I2C or SPI temperature sensors are just fine. Or analog temperature sensors and long wires, not necessarily a good idea unless you put some filtering. Okay. Soil moisture. And there I actually already selected a soil moisture sensor from Mauser. Adafruit Stemma soil moisture sensor. It's a capacitive sensor that gives you direct values for the soil moisture, and this is only for monitoring use. Okay. Ambient light sensor, cost less than €5. Okay. Digital interface, only for monitoring use again. Digital interface so that you don't need to worry about the making your analog electronics there. And then the big part is making the data logging. Since there are plenty of measurements, so there are something like 5 different temperatures plus couple of one humidity and one soil moisture, ambient light. You need to save the data locally on 1 minute intervals, and of course you know how to use boxcar averaging, so each sensor data should be a boxcar average of over 1 minute. Keeps track of time using real clock. Cost less than €5. You can find easily those from Mauser, preferably on dip package. Yeah, that will be easier to handle, but on the other hand, okay, those are usually simple packages also on SOIC or something like that. 1 week long non-volatile buffer, meaning some probably external EEPROM, or calculate how much you can actually use this EEPROM, or actually allocate some flash for virtual EEPROM on board. It might be enough, might be too little, but actually 1 week long data buffer. Or if you are adventurous, then you can use SD card. There is EM file component, and then you can practically save everything on data files, JSON formatted directly on data files. Okay, then download of this data from to computer using USB word bridge at rate 56,700. Okay, 57,600 is the correct value. Download this one. I selected that bitrate because if I want to do this, I probably will use another setup and longer the serial lines. Terminal interface, quite simple, since there are some say for debugging or something like that, and practically if a user sends question mark character online, then this device should print some identification information. For example, greenhouse controller number 1 developed by whoever. Okay, there's real-time clock. You need to set the time. The most practical thing, way to do it is to set the time from the user interface. Okay, time, and then also query the time, device time, and then set the date and query the date. Okay, and then if you press A, then it should actually, the device should send the data on JSON format, meaning date, time, all temperature in Celsius, air relative humidity in percentage, soil moisture as raw data, and light sensor data in lux, and okay, in JSON format. If you're using that the SD card, then this is also quite straightforward way to do it. Clear the device data logging memory. Let's see. Start a new data log file if SD card was used as a memory. If it was a separate chip, or you're using this device, the PSoC device memory, then you can actually just start saving the data on the top of the old one. Easiest way to clear. Okay. This project, I would say there's enough of things to do for 2 students. Quite many things actually, small details. It also have some hardware kind of stuff there. So 2 students or 2 or 3 students can share this project together. Sharing is caring. In addition, I would also recommend you to keep track on time you spend on this exercise. It should not go much above that, about 50 or 60, depending on how you define the ECTS. The 60 hours each. So keep track on how many hours you have spent. When it starts to go over this or if it looks like it's going over the nominal time, then you just pack everything together and make a report accordingly. Okay, same instructions as earlier. You would use the PDF document as a user guide instead of main.c, and basically you should have the user guide and anything which is needed to repeat this this device, or make another one of these. Okay, and all program files must be documented clearly enough for later development. Okay, so something to build on. Okay, so that's the greenhouse project. Then your own topic. Return of the project report is the same as previous, but okay, copy this as the template, your own project, rename it with your own topic, share it, anyone with link can connect, and then send email to me with the link to your project. So topic, I can then give you some comments directly on the design or on your own project description. What the project description should have, at least these. What are you going to do? Where is that project used? What is the usage? It must have some good usage. Why do you want to make it? It can be, for example, a hobby. I have a hobby. I do the video. I like working on games, so I decided to build a nice game based on this PSoC5 or something like that. Yes, it can be a game. How you are going to implement it? How you're going to meet the project deadline? Okay, this own topic. I have been teaching embedded systems for 20 years, and the most common reason for project not to meet the deadline is that the topic was students' own and it was way too challenging. So basically that's very important to point out on your this project description, how you are going to meet the project deadline. For example, put here a Gantt chart showing the schedule for your project, timeline for the project on each part. Okay, how and where are you going to get the required components? Are there something that you already have? Does someone need to order them? Are you ordering those yourself? Are you asking some donations from the manufacturers, or well, that's still a practical issue, how you are going to get the required components. Okay, for Metropolia students, I may spend a little bit of money on buying stuff, especially from Farnell. I can order these parts from Farnell. On the other hand, it would be quite hard to get it to you since since the coronavirus, the campus is closed. I guess that you have the same situation on Frankfurt, for example, too. Okay, so basically you can also build your project based on the devices you already have, and just think of a nice application you would like to try to do. Okay, so those are the 3 different topics. The project reports are the same. Project reporting requirements are the same for all of them, and basically the deadline for the project for everyone is May 30, end of May 2020. And you would use the same return form as on this exercise return, except that instead of link to main.c, you would have link to user guide. That's the best kind of project document, most useful kind of project document ever. So not really a classical this what was done and why document, but more like a user guide. Okay, so that's wraps up the whole course. So after returning these projects, it will take me for probably about a week or 2 to go through all of them, and you will get the you will get the markings on your course, passing of the course. Okay, good. So that's all for now. This is the last video for this course.